Hi and welcome to the Basic Assembly series. This time we are going to speak about Introduction to Branching. Motivation. So far we wrote some very simple programs. We used our computer like a pocket calculator. Maybe you remember some of the programs that we wrote earlier. For the most part they just read values as input and then do something very simple, something that you can actually do in your own pocket calculator. And then they immediately return the result. There is not much processing of the data. It is just a very simple process. Input, then very short calculation, and then output. We want to create more advanced programs. Maybe, for example, programs that run longer time, or programs that actually take decisions. Branching. So far, our programs ran linearly, from beginning to end. It means that no decision was made, and also the time it took to execute the program was proportional to the amount of code we wrote. That means that the program always finished very fast because it ran every instruction only once. Therefore, the time it took to run the program, totally speaking, is proportional to the amount of actual code that we wrote, which is not very interesting. That actually means that if we want the computer to do much work, we have to write much code ourselves, which is not what we expect as programmers. We would like to be able to do different things according to different results or values that we get. For example, maybe we want to run a certain piece of code on some condition, or maybe even run a certain piece of code many times. So far we only managed to run certain pieces of code only once, and maybe we want some kind of a loop, for example, to run the same piece of code many times, so that we can use the actual power of the computer. The computer has much strength regarding those kinds of things. The computer is very good in doing the same thing many times. Human beings are not very good at this kind of task. An example for linear program, which is something that you have already encountered. Actually, you have written some of these programs so far yourself if you have done all of the exercises. Let's look at an example. On the left we can see the assembly code, which does something pretty simple. Take a look at it for a few seconds, just to make sure that you understand what the code does. Okay, we can see that first it reads some value from the console. If you remember the function readHex that actually reads a number in base 16 from the console. Then it keeps this number inside ECX. Then again it reads another number from the console. And this time it takes the previous number which was stored inside ECX and adds it to the current read number which is stored in EAX. Eventually their sum is stored inside EAX. Then we add 1 to the sum using the increase instruction. Finally, we print back the result to the console. So actually we are going to get the sum of the two inputs plus 1 printed back to the console, which is a very simple calculation. If we try to draw this program in some kind of a diagram where each basic task is inside a rectangle and we have arrows between the rectangles, we get about something like this. First we read the number from the console, then we read another number from the console, we add the two numbers, we add 1 to the sum, and finally we write to the console the final result. This is a very linear style diagram. It is very simple. It goes from top to bottom, from the beginning to end. There is nothing very interesting that happens here in the middle. Let's take a look at another example. Branching illustration. This time we are going to try to do something a bit more complicated. Maybe you can see that we don't have actual assembly code here, and that is because we still don't know how to do this kind of things with the instructions that we previously learned. But we can still think about this kind of algorithm or this kind of program that we imagine that we want to have. For example, let's look at some kind of a very simple algorithm to check if a given number is a prime number. Maybe you have forgotten what is a prime number, so let me remind you. A prime number is a number that is only divisible by 1 and by itself. Some examples for prime numbers might be 3 or 5 or even 2 or 7. Basically speaking, just thinking about how to check if a number is prime, we can try to create a simple diagram to describe it. Let's look at this diagram. First we read a number into X from the console. That means that we actually read the number and then store it inside an imaginary cell that we call X. Next we initialize some other value. We are going to call it D like divisor, and we set it to 1. For example, you can think about X and D as some of the registers. Maybe X could be stored inside EAX and D could be stored inside EDX, for example. Next we increase D by 1. We calculate D plus 1 and store it inside D. Next, a bit of a different shaped place, a kind of a diamond, and inside the diamond we check if D equals X. Then there are two options. We can have as a result yes or no. If D doesn't equal X, which usually in the beginning it is not supposed to be equal to X because D begins with 1 and here it turns into 2 in the beginning. If it doesn't equal, then we are going to do this check. We are going to check if X modulo D equals 0. If it doesn't equal 0, we just go back to this task and again increase D by 1. And next, we check again if D equals X. If it is equals X, then we print no to the console. No, by the way, is the answer to the question, is the number X prime or not? So, we print no if we get that D equals X. But if it doesn't, again we check if X is divisible by D. If it is not divisible by D, we go back to this task of increasing D. But if it is divisible by D, that probably means that this number is not prime because we've found the number that X is divisible by it. This pretty simple diagram is a description of an imaginary program that checks whether a number X is prime or not. Those two diamonds are the actual constructs that we still don't know how to create. All of the previous tasks, for example, initializing a value to 1 or maybe increasing it, this could be done pretty easily, for example, using the move instruction. And the next task of increasing D could be done pretty simply using the increase instruction. However, we still don't know how to do this kind of things. For example, to check if two numbers are equal, and then conditionally do some task if they are equal, and do something else if they are not equal. For example, this kind of construct is what I'm looking for. This is what I want us to be able to achieve using assembly language. And in the future, in fact in the very close future, we are going to speak about how to create this kind of flow constructs in your own program. Eventually, you are going to be able to write all of this diagram and implement it in the assembly language even yourself. Let's talk about the EIP register. It is also known as the extended instruction pointer. Extended because it used to be only the instruction pointer on all the processors. and then when the processor was extended to size of 32 bits, the old register IP was extended to the new register EIP. So actually, the IP register is the lowest 16 bits of EIP. I remind you that EIP is of size 32 bits. Maybe you will actually remember the name. Maybe you remember the name EIP from the previous lectures that we had. In the past we only described it as a general register, but now we are going to learn about its special purpose. I also remind you that in long mode there is a register called RIP, which is of size 64 bits, and this RIP register actually extends the EIP register, but we are not going to deal with it right now. EIP contains the address of the current instruction, or maybe in some different formulation, it points to the current instruction. That means that you can always check the value of EIP, and EIP will tell you what is the current instruction which is being executed. EIP is actually the tool of the processor to know where he is, to know his location inside the code, in the execution of the code. If we want to execute code from a different location, we should change EIP. That's what EIP actually means. If we want to run different code from somewhere else, we just have to change the value of EIP to that other location. In 32-bit protected mode, EIP could not be changed directly. For example, if you are going to try to do something like this, like put this instruction inside your own code, move EIP EAX, it is not going to work. It is not going to work in the sense that the assembler will not assemble it because there is no such instruction, at least not in the 32-bit protected mode. We have to find another way to change EIP if we want to change the flow of our program.